Introduction to Solubility Equilibria. This is where, when equilibrium is reached between insoluble or slightly soluble salts and the ions it forms in solution. For more information, you want to be sure to visit AP Classroom, Unit 7. Additionally, there are more resources at Chemistry 2E, the OpenStax textbook resource for you. This is found in Chapter 15, Section 1. Nothing is truly totally insoluble, but sometimes such slight amounts are soluble that we generalize it and call the solution to be insoluble. For example, are oil paints. They are very slightly soluble in water, and as you can see, these are all salts, with examples shown here like Prussian blue, chrome yellow, and vermilion. To define what solubility is, we usually define it relative to a temperature. And I've taken a sample from a table from Wikipedia for some magnesium compounds. And at different temperatures, we can see at 0 degrees, magnesium acetate has a number 56.7, but at 40, it's up to 75.7. What do these numbers represent? We want to focus in on what the units are for these solubility measurements from this solubility table. Here, the units are given as grams per 100 milliliters of water or solution. It could be either water or solution depending on what your resources is. This is a little bit different from what we've been doing with concentrations before, where most everything has been moles of solute per liter of solution. So remember that when you're given solubility, it's not always molar solubility. Virtually everything in the table you see here from these magnesium compounds indicate that our lowest solubility is at a lower temperature and our highest solubility is at a high temperature. Sometimes we have missing data points for different compounds, but you can see that in general the solubility of a salt increases as the temperature rises. That's not always the case, but it is in many examples. When writing net ionic equations, lead chloride tends to be something we memorize to be completely insoluble, but placed in water, a small part will ionize into lead 2 ions and 2 chloride ions. And anything that comes to equilibrium between the together form and the ionized form, we can write an equilibrium expression for it. What we see here in writing the KSP would be that we have our lead 2 ions, the concentration of that, and that again would be in moles per liter, times the chloride ion concentration squared due to the coefficient of 2. And we have solid lead chloride. And we cannot put a solid, so sometimes you might see a denominator of 1, but technically that's not even necessary. There is no concentration for a solid. It's not in solution, it's not shown together, or as in brackets, it's not a gas pressure because it is a solid salt. So our equilibrium expression is simply the equilibrium constant with the subscript SP for solubility product constant is the concentration of our products raised to their exponents. For example number 2, let's look at silver sulfate. It dissolves into 2 silver ions and 1 sulfate ion. Here we can, as we've done in the past, set up an icebox, an ice table, where we can look at the different pieces of information. We do not have any initial concentration of the solid. We have no source from a different solution. If we're just looking at an aqueous solution, there's no other source of silver or no other source of sulfate, and we're going to experience some kind of change here. It will definitely be an increase in silver ions, and we get twice as many silver ions as we do sulfate ions, so we'll have 2. Instead of using an X, sometimes we use an S to represent the fact that we're dealing with solubility. And this would also be an increase by 1s. So at equilibrium, our values are 2s and s. Setting up our KSP, we would find that the concentration of the silver ions squared times the concentration of the sulfate ions would allow us to have 2s needs to be squared times s. The math for that would be 4s squared times s, or 4s cubed. So our KSP value would be 4s cubed. If we knew the solubility product constant, we would be able to solve for our missing amount. The units for that, since it would be in concentration, would be in moles per liter.